Okay.
Hello, Max.
So welcome all to the second talk of this afternoon, and it's my great pleasure to introduce Maria Soledad Aronna. For us, just Soledad Aronna, as a matter of fact, or just Soledad. Soledad has been Soledad has doing his graduating work at Universidade Nacional de Rosário, got a PhD from the College Polytechnique, and then she has go out around the world. She has she was a Marie Curie fellows, I think, in Imperial College and Padova, and she also went to IMPA as excellence postdoc. Now she's for some time now she's at FGV, and she very recently has been awarded being a CAPS Humboldt Fellow, and also she's a CNPq Research Fellow, and she's a young research scientist from Rio. In the sense that not just to say that she's a young research scientist, she has a fellowship from state, the Rio de Janeiro State Scientific Agency. Soledad has done a lot of work in control theory and more recent, not that more recently, I mean, so for some time now, in mathematical epidemiology, and the opportunity to join some projects with her. But we're not working together, but we're in the same project. And this year, COVID has showed us the importance of modeling in mathematics in the health sciences. And Soledad will bring us back to another problem we have and kind of forgotten because of the pandemic, is that this vector-borne disease. They are still there. These two cause a lot of issues, particularly here in Brazil. And Soledad has made a lot of nice contributions to this. And yeah, and I should then, look forward for your talk, which is modeling and analysis of Sterile Insect Technique, implementation strategies for vector and pest control. Soledad, thank you so much for coming. The screen's all yours. Thank you.
Thank you. Thank you, Max. Thank you, Juan, and all the organizers for the invitation. So, yes, I will talk about insects. I have worked a bit on COVID modeling last year, but I think that everybody had enough with COVID modeling probably, so I chose to go back to my original problems of vector control. Okay. So this is a joint work with Yves Dumont from Sierrat, France, Montpellier. He also has a position in Pretoria, South Africa, and now he has moved to La Réunion, the island of La Réunion in France. So, so this is the outline of my talk. So let us see first. So this sterile insect technique that I will talk about, so I will call it SIT, to be short. So the idea is to use radiation. So it's a method that has been applied for, like, let's say, a lot of years, like many decades. So the principle is that the use of radiation to generate sterile male insects. Okay, so in the laboratory, these sterile male are created and then they are released into the wild. Okay, so in the wild, these male that are sterile, they mate with white females, and these females do not produce offspring, or they produce less. Okay, so if we have 100% sterility, they don't produce any offspring, they don't have descendants, but there can be a residual fertility. Okay, that is what we are going to treat in this model. So the aim is to use this technique to reduce the size of an insect population. As I put in the title of my talk, I said pest or vector control. So the idea is to reduce the size of an insect population. It can be an insect that is a vector that is the responsible of the transmission of some disease, for example, dengue or yellow fever, or it can be a pest in a crop, in a plantation, for example, like these fruit flies. Okay. So let's see, continue. So that's the picture of the International Atomic Energy Agency. So the idea is that we generate these insects, and then they are ionized using radiation to sterilize the male, and then they are released in the nature by drones or by airplanes, and then they compete with the male that are wild, that are in nature, to fecundate the female. Okay, and so the encounter between a sterile male and a white female doesn't produce offspring, or it produces less. So let's see. I put some project examples. These were my co-author, the co-author of this talk, that is Yves Dumont. He's working on these two projects in the island of La Réunion, the Reunion Island of France. So one of them is to control Aedes albopictus, that is responsible for transmission of many diseases. And the other one is to control this fruit fly, that is Bactrocera dorsalis, that is responsible for, it's a pest in many plantations in hundreds, in a lot of countries around the world. So actually, so of course, what is the idea of controlling? Okay, it's if we can the benefits of controlling this fruit fly is to have like health plantations. So it has an impact, a great impact in economy, and the same for, of course, controlling vector-borne diseases. So I will go to, let's say, some considerations about this sterility. So the idea is that to achieve full sterility, that means that all the males that are ionized are completely sterile, we need high amounts of radiation. But the problem is that high amount of radiation has an impact in the fitness of the mosquitoes. Okay, so there has to be a balance between these actions. And lower radiation, of course, has a reduced impact in fitness, but it can generate partially fertile males. So imagine that you release mosquitoes or insects, and some of them are still fertile. That's a problem, because as you will see in the numerical simulations at the end, we have to release a lot of insects to deal with the population. So it's not a good idea to release. It's very bad when it happens that we release a lot of insects that can reproduce. Okay, that's the idea. So the goal of this work is to propose a model for implementation of these sterile insect techniques, okay, that takes into account this partial sterility case. Okay, so first, the model. I will just say that what I will present here is only ODE, or ordinary differential equations. I haven't worked in PDEs in this in this framework, but of course there must be many PDE interesting extensions and improvement, maybe improvement like a special distribution that can improve these results. Okay, but I haven't worked on that, so I work with the toy model in ordinary differential equations. So let's see. This is a model for the mosquito population. So this is the wild population. Sorry, I said mosquito, but when I say mosquito, it's insect. It's just that I am so used to work with mosquitoes, but that I always say mosquito. So insects in general. So we divide the population in two, male and female. So first, forget about the sterile for a moment, and I present the model without SIT, okay, without the sterile insect technique. So we have male and female population, and so this is the two equations that they follow. So there are some parameters appear. So the sex ratio is R. So we have R on one equation and 1 minus R in the other one. So the reproduction is proportional to the amount of female in the population. Okay, and there is a competitive factor that is the exponential of minus beta m plus f. So the idea to use the iPad here is to be able to write. So let's say, great. So this is, let's say, this term is for competition between the individuals. Okay, and so these two terms are mortality. Great. And of course, so we have the sex ratio R, and here rho is the mean number of viable eggs by female per day. So day is the time unit. Great. This is very easy. Okay. A model for the wild population. Okay. So we have to do very easy assumption, that is that the population is viable. Okay. So it will not die alone. Okay. So because that's the usual thing, and we want to treat that population. But in terms of mathematics and parameters, what does it mean? It means that these numbers that are called the basic offspring numbers that are calculated like this. So I will use another color to contrast a bit. Okay. Basic offspring number, that's the mean number of descendants that each female produces in its lifespan. So those numbers are assumed to be greater than 1. I will say that in the next slide. But in terms of those numbers, we can compute the unique positive equilibrium of the system I have just presented, that is given by these two formulas. Okay, and one easy result is this one. So if the basic offspring number of the female is less or equal to 1, then the trivial equilibrium, that is the origin, is globally asymptotically stable, so without SIT, so we don't care about, of course, about that situation. Okay? But if the basic offspring number of the female is greater than 1, then that equilibrium that is computed there is globally asymptotically stable for the system without SIT. Okay, so of course, basic assumption, we assume that the population is viable, so we put that both the female and male have viable populations. Okay, that's easy. Let us continue now. Okay, so we take those two equations that I presented, and we add this sterile male, that they follow a different, another dynamic, okay, that is this one. So the idea is the following. We have, so male, female, that's M, F, and then we have this sterile male. They are released, and they do not reproduce themselves in the population. They are released, and they mate with one female, and then they die. Okay, that's the role in society for them. Great. So we have new parameters here. First is the mu S, that is the mortality for the sterile male. Then there is this gamma, that is the competitiveness index of sterile male mosquitoes. So let us see what does it mean. So before, we didn't have this blue fraction in the model. That's what we are adding when we add sterile male. Okay, so before the births were proportional to F, that were the female. Now we have this fraction. Okay, so if gamma is equal to 1, imagine if the case gamma equal to 1, epsilon equal to 0. In that case, we will have this fraction. Okay, that's great. So female will encounter a fertile male with this probability. Okay, but now, and that's what happens if the competitiveness of the sterile male is complete. So now what we do is we add this gamma, okay, and some residual fertility here. That's the idea. Okay, so we get this fraction to compute the new proportion of the new probability of a female having offspring. Great. So, and now the sterile male, this is the dynamics. Here, the third equation. So they die with this rate, and they are introduced with this rate, lambda. Okay, lambda here, I will not say anything about it. Here is the constant. Then during the talk, it will be sometimes a function dependent on time. It can be a function depending on the state. If we use this closed loop or feedback releases, that means releases that depend on the state of the system. Okay, but so for the moment, it is some lambda, that is the release rate. Great. So, release strategies. I will talk about two kinds of strategies. We can put many categories, okay? So, but mainly there are two kinds of strategies. This open loop, that they do not depend on the state of the system. They only depend on the parameters, okay? And yeah, I will show them later. And this closed loop that are more interesting, that are adjusted depending on the state of the system, okay? So let's start with, I will put everything in one slide, right? So I had forgotten this slide where I explained a bit more in detail what I mean with this open loop and closed loop strategies. So open loop, I will present two things. First, some release strategy that will have this form, that is a function of time, okay? Okay, it's like an open loop control, we can think of that. Okay, and then the idea is that, so what is the idea? We cannot be continuously releasing insects. Okay, in practice, what we usually do, what it's usually done, is to go to the wild once every week or once every 2 weeks, okay, to release mosquitoes. Okay, and that, in terms of differential equations, will be modeled by us by an impulsive differential equations. But what we do is the following. We look for strategies in continuous time, and then we use that information to construct strategies that are impulsive in time. That's the idea. So continuous in time will have this form, okay, and impulsive in time will be like that. So at each time n tau, so tau will be some period, okay, at each time n tau, for an integer number, we will release some amount of insects that is a quantity lambda, okay, or it can be even lambda of n, okay. Great. Then that's open loop. Closed loop. In closed loop, the idea is that we depend on time. Sorry, we depend on the state, and here we will have two types of strategies. Again, continuous in time, and the other one that is impulsive. It's the same process as we did in open loop. Okay, let's start with some calculations. Okay, so we have the following. So we assume that we do a constant release of lambda. Okay, so in that case, we look at the equation of the sterile male, that is this equation, okay, and we assume that we reach the equilibrium there. It's not, it's very easy to reach the equilibrium, actually. So the idea is to then, if we reach the equilibrium, that is this number here, ms star, okay, we can replace by that quantity in the system of equations, okay? And to reach that equilibrium is easy. We can make some short calculations. We have to release a bit more than lambda for a short period of time, and then we can achieve this value, and once we achieve that value, we keep on releasing lambda, and we maintain constant the sterile male population. So in that case, we simplify the model, and we get to this model, okay, where I replace every appearance of ms, that is the sterile male, I replace it by the value of the equilibrium, right? So for this system, what we want is to steer the population, this Y population mf, to 0, okay? So we want conditions on lambda. Lambda is the release rate that steer the Y population to 0, okay? So we got this by doing an analysis of the equilibrium, depending on the parameters, we get to this proposition, okay? So let us remember, epsilon was the residual fertility. Okay. Fertility. Okay. So the idea is that this residual fertility, to make things work, to this SIT, sterile insect techniques to work, it has to be bounded. Okay, and it has to be bounded by this number that is the inverse of the basic offspring number for female. Okay, so the bigger the offspring number is, the more restricted epsilon is. Okay, so if this epsilon satisfies the constraint, then there exists a threshold for lambda. Okay, such that, so I will do this picture, it's easier. This is the threshold, okay? Such that, so here we have two equilibria, here we have 1, 2, and here we have no positive equilibrium, okay? That's the idea. So in this region, that is the region that we're interested in, the only equilibrium is 0 and is globally asymptotically stable. So we're interested in this situation. So we will use releases. If we use this constant and time continuous strategy, we will use releases that are bigger than this threshold. But as an observation, I present this, the second item of the proposition. It is that when the residual fertility is bigger than this number, okay, the SIT can fail, or usually fails, actually, what we saw in the simulations. Okay, so there is a positive equilibrium that is is positive. That means that both components are positive, so the male and the female, that attracts many of the trajectories. So we cannot control the system. We cannot exterminate the insect population in that case. Okay, so we will always keep this hypothesis. Right. So now let us see what happens with this, how we create impulsive periodic releases. So now the dynamics of the sterile male are like this. So the idea is that at each time n tau, okay, we release mosquitoes lambda, or lambda, it can be lambda or lambda n. Okay, great. Right. In that case, the population of the sterile male, so it is important to see that the population of the sterile male can be computed without taking into account the wild population. Okay, it has its evolution because, as I said before, they enter into the population and they mate and die. That's all. So this is the dynamics, and releasing lambda, okay, at each time n tau, the population MS approaches this periodic function. Okay, so to study this this system, that now we will do periodic releases of lambda, we study this system where we replace the sterile male population by this periodic solution. Okay, and again, so what we want is conditions for lambda such that 0 is a globally asymptotically stable equilibrium of this system. Right. So we do some calculations. We take the shape of this system is nice because if we, I will go it back. So if we look at here, we have F multiplying here and F here, so we can write the equation for F in this form, and we will use this several times. Okay, so once we write the equation of F in this form. So in each interval, so in each n tau, we will release the insects. So at each of those intervals, we can do this estimate. We can write this estimate. Okay, so the size of the female population will be the size of the female population at the beginning of the interval multiplied by this. Okay, that is an integral here. What is easy is that the only thing that is dependent on time is this function, okay? And to get from one equation to the estimate, we replace this function that appears in the first equation, the original equation, by its maximum, okay? Great. And so when we get that what we want, sorry, is to have this integral, the exponent, sorry, negative. If we have a negative exponential, so what will happen is that the female population will decrease, okay? So we compute here, and we do the calculation of the integral, we get this, okay? So that's what we will impose, that number is smaller than 0, okay? That is negative. Remember that I was integrating, and the only time-dependent function was this ms periodic, so I integrate that. So, and I use this notation, so we use this notation to denote the average of that function, okay? So this inequality is inequality of real numbers, okay? And again, it is important that this number is positive, okay? It is important that this number is positive to be able to find conditions for this periodic solution to satisfy this inequality that is smaller to 0, okay? Great. So again, we find again the condition that the residual fertility epsilon has to be smaller than that number that is the inverse of the basic offspring number for female. Right. So again, going back to the original notation, so remember that we had lambda, that was the release rate. This generated this function, okay, that was dependent on lambda, okay, and then this function was inserted in the system. So what we do in this result is we found sufficient conditions for lambda for the periodic system to have the origin as a globally asymptotically stable equilibrium. Okay, so if lambda is greater than this value that we found here, that is written in terms of the parameters, then every solution of the impulsive system where we put the periodic solution converges to 0. So that means that if every n tau days we release lambda, okay, we will achieve our goal of eliminating the insect population. Right. Closed loop. Now we go to strategies that depend on the state. These are more interesting, and we will see that these strategies give the less amount of mosquitoes to be used, but because we will adapt. Okay, so this is an easy trick, let us say. What we do is the following. So these are S and M are two scalar functions, so they are related by some scalar value that is kappa. So kappa is what is usually called like a feedback gain. We will try to find how many sterile insects we want to have in terms of how many males, white male we have. Right? So the interesting thing is that when we replace the appearances of MS by this formula, that is MS equal to kappa M, we replace that in our system, we get this system. That is a bit simplified. It's simpler than before. And what we get is this equation again. So see that we use the fact that this is the shape of the equation for F, for the female. And here what we have is this function of time. Right. So we want to reduce the population. Okay. So actually, if we impose that this quantity here in the bracket is negative, then the female population will decay exponentially, and the same will happen for the male population. Okay, and that will be useful to achieve the goal. So what we do is we impose, we will find this kappa to have this quantity less or equal than minus theta, where theta is positive. Okay, so doing that is equivalent to choosing kappa, okay, such that this holds. Perfect. Okay, so once we set theta, so we can think of theta as the decay rate for the female population. So once we fix theta, okay, we have a lower bound for the gain. So this is the feedback gain, kappa. Okay, that is completely reasonable from a practical and from a mathematical point of view. Right? So with this feedback gain, we will do some recipes. We will use this feedback gain to construct the releases. Great, that's the idea. So in continuous time, it is very easy. So we just say, assuming again that the residual fertility satisfies that constraint, okay, here. Then we need to choose theta satisfying this. This appears in the calculation. Is very it's already evident in the fraction that I showed in the previous slide. Then so we can choose theta here such that theta plus epsilon is smaller than 1 over NF, and then if we chose, if we have that the sterile population satisfies this inequality, where kappa is the function that I showed in the previous slide, then every solution of the closed loop system converges exponentially to 0. That's what we want. Okay, and this is in continuous time. So the idea is that we use this continuous nonlinear feedback law to construct impulsive strategies that are more applicable, okay, are easy to practice, to implement in practice. Right. And again, I want to make an observation. So this was the residual fertility. So after ionization, we have this residual fertility in the population that we will release. Okay, and this was a bound. So minus theta was the decay rate for F, decay rate for the white female population. Okay, so see that if the residual population is too close to this threshold, NF minus 1, then we cannot make the female population decay too quickly. Okay, so again, the difference between the space, let us say, between epsilon and this bound NF minus 1 gives us freedom to make the female population go like very quickly, go to 0 very quickly or very slowly. Of course, we want to make that quickly, okay, quickly and cheap, not to release too many mosquitoes. So using this calculation for continuous time, we can write, we can construct strategies for impulsive time, okay, for this continuous time. The idea is that, okay, so we have here, when we do the calculations, we have this new constraint, but actually it's the same. Here, this constraint is the same as the one before. It is the same if the mortality, like this, if the mortality of the sterile insects is greater than the mortality of the female. That is what's commonly happens in practice. Okay, so but as we didn't want to impose that additional hypothesis, we put it here, but actually in practice it's the same. So imagine we have the same constraint as before. So in that case, if we take at each time the releases satisfying that inequality there, then so if we do these releases, then we can steer the population to 0, the wild population to 0. And as we can notice here, I put here synchronized measurements and releases, okay? That means that at each time n tau, we measure the population, the female and the male population, and we release. But we can do a bit, something a bit cheaper, let's say from an interventional point of view, that it's not measuring all the time. So measuring at each p periods. So we measure at np tau and we release at n tau. And in that case, we can calculate, once we measure, we can calculate the next p releases, okay? And we have this formula, I will not enter into details, but everything is computed from the theorem in continuous time, okay? So if we release following this inequality, then we can eliminate the population, okay? Right. So the last observation before I show the numerical experiments is the following. So here is what we called in the paper long-term control strategies. So the idea is the following. We use all the calculations that I did before, that I showed before, to steer the system close to 0. What is, so of course, the 0, if we release enough mosquitoes, enough insects, the 0 is globally asymptotically stable. That's what we saw in all the theorems that I showed before. But the problem is that we will not reach 0 in a finite amount of time. Okay, we know that. So we will go here and we will be close to 0, right? But if we stop controlling, if we stop releasing male mosquitoes, then as soon as some eggs or larvae or some adults remain alive, the population will increase and will go back to the original positive equilibrium, and all the effort will be wasted. So, but the idea is the following. We will use the strategies that I showed before to steer the population close to 0. So that's why I will show here. We will steer the population close to 0 in some rectangle that I will show how to calculate, how we calculate it in the next slide. So we steer the population here, and once we are here, the idea is that in each period we release just some insects to keep the population stable. Is to maintain to maintain like the effort, okay? Just to not to go back to the original. Sorry, it's to maintain the control. I couldn't find the word. Control was the word, right? But that's cheap because for several weeks, let's say 20 weeks, we release a lot of insects. Okay, so and then we keep the insect population very, very, very low. In terms of diseases, if the insect population is low enough, it's small enough, then we will not have epidemics of any vector-borne disease, for example, any of the diseases transmitted by that insect, of course. Okay, great. So I will finish. This is the last slide before the numerical calculations. So here, what we do is that so we take this system that I had before, and we observe that this is bounded from above, okay, by another system where we put a lower bound for this periodic solution, okay, for this periodic solution, okay. So now we take the system, and this system, okay, where the sterile population is fixed to this value, this system has two positive equilibria. We had already calculated this. It has two positive equilibria, so we use this. Okay, and the idea is that two positive equilibria that will have this form, E1, E2. Okay, right. The idea is that this E1, this rectangle here, is included in a region where the system is monotone. Okay, here the system is monotone. Actually, I should put like this. Sorry, I will erase here. I will let us see the slide. Sorry, here is the information. So, if these are the female, here the system is monotone. It's monotone compared to the system. I will explain that. Okay, and so, and the region where we want to enter is this one. Okay. So what is a monotone system? For a monotone system is, in this case, I will not explain in general. So, but in this case, it means that if we have two initial conditions, okay, that are ordered, okay, let's say the order here, we're in R2, is ordered by components. So both components are one less or equal than the other one. Okay, I will put like this, and the first component is less or equal than the first component of y, and the second of x is less or equal than the second component of y. Then it means that the solutions of the system, I will put like this, starting here, will keep the same order. Okay, great. So once we move to a region that is this region where it's monotone, and we enter this box, we can stay in this box, releasing a very small amount of mosquitoes every week to maintain the control. So that's what I say here, the long-term control strategy. Okay, some finite phase with large releases, and then let's say an infinite time phase where we keep controlling every week or every 2 days. Right. So this, what I will show now, is the numerical part. Like, the idea is that to do the numerical part, what we did is at each time that we have to release, we compute the minimum between the closed loop and the open loop strategy. That's to minimize, using our strategies to minimize the quantity of sterile males to be released. Okay, and we will see, we will compare the total amount of mosquitoes that we released and the amount of times that we had to release. So let's say, let's show it here. So I would take this Aedes albopictus example. Okay, these are the parameters. Okay, great. So if we do the calculation, so here we have a bound for the residual fertility that is 2%. Okay, so we compute for the full sterility case, that is when epsilon is equal to 0. Okay, and so what I said before, there are two values that are important in each intervention. One is the total amount of sterile males that are released, and the other one is how many times we release. Okay, so we made several tests, sorry, and so for example here, remember, P was whether we were measuring and releasing at the same time, and if P is equal to 1. If P is equal to 4, it means that we release 4 times and then we measure, we release 4 times and then we measure. Okay, so we have less measurements than releases, of course, because measurements are also expensive. So we can see that if we compare we compare two methods. This feedback control in both cases. We compare linear control, that is, sorry, I removed that. There was one equation. So I will explain very easily. 1 second, just to. The linear control was what was present in the literature before. I shouldn't have, sorry, but it's easy. So, in the, sorry, 1 second. Boom. Sorry, I forgot to, let me remember in 1 second what was the idea. Okay. 1 second. Okay, so the idea is that I'm white-minded. It's horrible not to have public here. I'm sorry. I should have. I should open. 1 second, please. Give me 1 second. No, I will finish the idea, and then I will go to the other slide that I prepared, and I raise here. I'm sorry. So the idea is that to compare. We compared this linear closed loop control that was present before in the literature, that was this similar idea, but then it was not that well adapted to the measurements in each case. I will show it in a few seconds. Sorry for this. I will go here. So we're here. We are in the full sterility case. And then we show that the best solution, so we do several tests, and we arrive to these 2 solutions in blue, okay, that are the best ones. And we can see that this nonlinear control that we show here is use less mosquitoes, okay, so it's 10 to 5 here and 10 to the power 6, okay. So and I compare both strategies like numerically. So give me 1 second, because can I take 2 minutes max? Sorry for this. And then I will finish.
Yeah.
Yes,
sure.
Okay. Because I'm already finishing, but I did this mistake of trying to cut the exposition, and I cut too much. Sorry. And I need the formula for the linear control for this last part. If not, it doesn't make sense. Yes, right. Now I remember what was the formula. So sorry for the waste of time. So we are here. So the linear control is, the idea is, I will show it here. So we have this function kappa of x that I showed before, okay? So our feedback was this way. So ms of t is equal to kappa of kappa multiplied by m, sorry, multiplied by m t. Right. This is the nonlinear, what we did in this paper. And the idea is that in previous paper by my colleague Yves Dumont and Pierre Bliman and Olga Vasilieva, they did something like this. They do a linear feedback, okay? And so the gain is constant and is actually equal to our gain at 0, okay? That's the idea. So we compare and we show, like, we observe numerically that the strategies that we constructed work, okay? And so this nonlinear strategy works better in many cases. And so this is for the full sterility case that was already treated in the literature. So we have these pictures. So see that blue is male, red is female, that's for the wild population, and then these things with the jumps, of course, is the sterile male population. Okay, and then for the residual fertility case, that was what let's say the aspect that we added to the model. We get this this comparison of the results. Okay, so here it's a bit harder to compare. So actually, the linear case works, sometimes works a bit better because we have to go less times to the wild, but then the total amount of mosquitoes is smaller here for the nonlinear case. Okay, but in any case, so we showed analytically and now numerically that they control the population. Okay, and just to end with, I did this last numerical experiment to compare what we are doing with the optimal solution. Okay, because are we releasing too much? That's a natural question. So I did this toy optimal control problem and I put it in a solver. That's all. And so the optimal control now, U is the releases per unit time. Okay, and we minimize the total amount of mosquitoes to be released, and we release in continuous time. So something that is much more efficient but less practical. Okay, great. If we do this, and we compare with the releases in the releases that we use in closed loop and impulsive. Okay, and it's interesting because in this picture what we have is, so in blue we have the white male, so here. In green the sterile male, and here is the accumulated sterile male. So we can control the optimal control. If we have to compare the accumulated, of course, this is the gap here between the accumulated in the impulsive and the accumulated in the optimal. It's only 10%. So with those strategies that we're creating, at least numerically, we are only like 10% away from the optimal thinking of the optimal control problem. Great, and with this I finished. So we did this model with for SIT when partially fertility or residual fertility occurs. We have a nonlinear feedback. We propose a nonlinear feedback, and okay, in many cases the nonlinear feedback is better than other strategies that were presented in the literature. And with this toy problem of optimal control, we observe that the cost is quite good. Okay, it's not, we are releasing not too many. That's all. Thank you.
Thank you, Soledad. Thank you so much. This is a very nice talk. And yeah, open for questions. Comments? Okay. If nobody has a question so far, I have one or two. I start with one. So back in your model, there's one thing that maybe have said about something and I just missed it. Competition is always between males and females. The sterile males do not enter into this competition. Any reason for that?
What? Sorry, again? Can you?
Oh, so if you look at your equations in the exponential term, which is you mentioned it was a kind of competition. The beta
yes, yes, you're right. Because I think it's the larval competition. So sterile male will not compete. It's larval competition.
Okay. So it's really okay.
Yes, good question. Yes. So they don't enter in the exponential. Sorry, okay. I can go back.
They just release it. Okay, yeah.
Yes, they are adults when they go out.
Okay.
So the model must be somewhere in my slides. Okay, yes, there, for example.
Yeah.
Yes. Okay.
That's the reason. Right. Thanks for that.
Yes.
Questions?
So yeah, sorry, I forgot the linear case. It's not, I mean, it was not the main goal of the talk to compare the results, but then with the numerics, we did compare the result, of course. I mean, and in sometimes the linear works, but it really depends on the cost of the intervention. So we didn't put that, we didn't like weight it, because you have to put a weight to going back each time you go back to the wild and each mosquito, each insect you release. We didn't do that in detail. Okay, we just wanted to see if numerically things work and how they compare with strategies that were present in the literature, and of course to add this residual fertility that is important. And it actually shows that the last observation that I make, because I like to talk about this. We can see, so if this is with epsilon equal to 0, so it's 10 to the 5, okay? And you can go out 10 times. If you have residual fertility of 1.5%, okay, you have to go like to use 10 to the 6 or 10 to the 7, depends on them, and to go like 30 times to the field. That's so a bit of residual fertility is a disaster for the intervention.
Yeah, that's no, that well, I won't say interesting results, but I can see it from the point of view of control, but it's a really important one. I mean, it's
yes,
definitely.
Yes. So maybe it's better to lose a bit of competitiveness of the mosquito, but to have full sterility.
Yeah, that's what you're teaching us, and that's exactly.
Okay. Thank you. Sorry, you were going to say something?
Yeah, I mean, I have one more question, and if not, which is the following. I mean, you have this very nice strategy to take off the system into a phase space where it is monotone, and then there you can use very small interventions. So actually, there are two questions. I mean, one is that would work. I mean, that always work. I mean, if I can, I mean, that's something more general. It's more related to this particular system. And could you give some hints why it works? I mean, it was not really obvious to me that bringing into that would allow you to do that. I don't know if it's
Okay. Let's see if I have it written. If I can show. Let's see here, because there is here. So let me think a bit about this. So if the idea is that we will not, since this system is monotone, the idea is that we will never go out of that box. Okay, there are two equilibria. The box is between two equilibria that are ordered. Okay, with the order that gives them monotony, and we will never go out of that box if we keep on controlling, like if we keep the same system, because the system is monotone when we fix the releases to a certain value. Okay, that is between this is here in this case actually. So we put lambda in this case, and we'll never go out of that box that as we wrote in the system, and as we wrote in the paper. Sorry, that's the idea.
Okay, great. That's a very nice idea.
Yes, it was. I have to say, that was before. If that is my colleague, no, a co-author already used it in a paper before, and so here we mix like a lot of strategies to get something better, of course. And he implemented that in another paper he did before. Okay.
Fantastic.
Hello, Alexandre. So I can see you.
Yeah, hi.
Yes.
Can I ask a question, Max? Well, very nice work, Soledad. Congratulations. So maybe I got it wrong, but it seems that
can you speak a bit louder, Alexandre? Your voice is quite
sorry,
slow.
can you hear me?
Yes, but
maybe I got wrong, but it seems that you use epsilon and gamma, the competitiveness and the sterility, as independent parameter. And it seems from your explanation that they are not in practice. How do they relate? I mean, do people know about that?
yeah, okay. Of course, they are related. I will not like put. I didn't want to put like gamma as a function of epsilon, something like that. Of course, when the notation is too complicated. But there have been experiments where they say, okay, let's see. Yes, there are experiments where they know, okay, with this amount of radiation, we get like, let's say 2% residual fertility, and we estimate the loss of competitiveness like this. But these are really isolated experiments for each species. Okay, it's very hard to estimate that. So once if you get to the point to do an intervention, of course, it's natural that you have already studied the species a lot, and many experiments have been done. And for one particular species, I imagine, in many cases, they have estimates of gamma and of epsilon. Yes.
Okay. Thank you.
Yes. That is a good question.
Thank you, Alexandre. So any more questions? If there are no more questions, then okay, thank you so much, Soledad, for this wonderful talk. Thank you also, Nicholas, for this very nice talk. So it was a wonderful afternoon, going from PDs and viscoelastic fluids to mathematical epidemiology. And thank you all for coming. And in 1 or 2 days, the videos will be streaming in the seminar channel. So if you haven't missed a beat, or you didn't understood some passage, you have all the time to go back and look at again. And for the 2 weeks, we have the next edition of the seminar. And so till there, I hope you all stay well, and see you in 2 weeks. Thank you.
Okay.
Thank you all.
Thank you for the invitation. Thank you for coming.
Thank you so much.
Ciao.
Ciao.